Alright, let's start talking about multiplying vectors. We're going to be doing that a lot in this class and especially in your future. There's three ways. One is very simply to multiply by a scalar. So multiply by scalar, and we'll say that scalar is some s. So if I had some vector a is equal to some x component, and also has some y component in the j direction. Could have a k also, but for simplicity we'll leave it here. If I wanted to multiply s, let's use parentheses not to confuse this, and you'll see why. S times the vector a, where s is a scalar and just a number, it's not a vector, then we would just multiply s by the whole vector, which would give us s times a sub x in the I direction and s times a sub y in the j direction. Alright, that's easy. Okay, so if you're multiplying by a scalar, you just literally multiply the two things together. The second one we're going to cover in this video, the third I'll cover in its own, is called the dot product. Alright, so to explain this one, let me go ahead and say we have some vector a like this, and maybe some vector b like this. I would say we need to find the dot product of a and b, or say a dot b. A dotted into b is equal to the magnitude of a times the magnitude of b, and these are just the magnitude, so don't actually need the vector sign, times the cosine of the angle between here. So if you notice, we end up with a scalar. So it's the only way to multiply vectors that actually gives us a scalar back. And what it is doing, you can think of it in two ways, and I'll help you with an example using force and displacement in a moment. You've worked with work before. I know you have in high school. But what's it doing for just two generic vectors a and b? If I projected a 90-degree angle from a onto b, that would give me a cosine theta. And then what we would be doing is multiplying these two vectors together, b times a cosine theta. That is equal to a dot b, the dot product of a and b. Another way to think of it would be to take those vectors, redraw them, a and b, and if I projected at a right angle the amount of this one, that would give me this vector as b cosine theta. So we can think of it as the magnitude of one vector times the scalar component in the direction of that first vector, or vice versa. So one more time, the magnitude of one of the vectors times the scalar component in the direction of the first vector. So a good example of this is actually when we look at work. By definition, it is the integral of a force vector dotted into a displacement, and we use dr because we integrate from some r1 to some r2 to get our actual displacement. So what does that dot product mean? Well, imagine a block with some mass, and it's confined to only move on the surface in the x direction. So it's moving in this direction. And the reason it's moving, we'll work lots with this, I just want to give you an example, is because some force is being applied. That force is not being applied in the same exact direction as the displacement, however. There's some angle difference right here. There's some theta. So when we find the work definition, by the way, can actually reduce down to, just like the dot product, F times the displacement cosine of theta. And what that's doing is putting the projection of F onto the displacement and gives us a way to multiply it. Basically the effectiveness of the force in that direction times the direction, and we get a scalar quantity back, work. That's my best example I can give you all to understand what the dot product is for. Now we can also say what is the component of the x direction displacement on the force. So we can literally say d times f cosine theta also. This one doesn't make much sense to me. That one does. Depends on what quantities or what vector quantities you're working with though. Okay, check my notes real quick. Okay. So the dot product, so A dot B, is also commutative. It's equal to B dotted into A. You can always flip them around and make it a little easier on yourself. It also shares properties like the distributive properties. So if we had some scalar, some vector A, and we wanted to dot that into B plus some other vector C. We could add the vectors together first and then dot them. Or if we, for some reason, made the problem easier, we could say that's equal to A dotted into B plus A dotted into C. So you don't need to memorize this one yet. You need to know this other stuff and the prime definition for the dot product, A, B cosine theta. Some special little notes though. If we dot a vector that is perpendicular to some other vector, in this case A dot B is going to be equal to 0, and that is because the cosine of 90 degrees is 0. What happens when the cosine is 0 degrees? Think about it. So that would be A dotted in, make it different color, to B. Well, A dotted into B in this case would be, let me scroll up, the magnitude of A times the magnitude of B times the cosine of 0, and the cosine of 0 is 1. So we just get A times B. A dotted into B, and that's only when they are in the same direction. And once again, if they are perpendicular, that means, the cosine of 90 ends up being 0. So the definition of our dot product, A dotted into B equals the magnitude of B times the magnitude of A cosine theta. The cosine of 90 degrees is going to go to 0, making the whole thing go away. So if they're perpendicular, it's 0. If it is in line with each other in the same direction, you don't have to consider the angle at all. So basically a dot product is more effective when on each other when they are in the same direction. Another couple quick notes. When we're taking a dot product of a vector, let's say we had some A, it's equal to AX in the I direction plus BX in the J direction. Let's go ahead and give it, AX, this is not a BX, AY in the J direction plus some AZ in the K direction. We'll give it a K, and we'll say some B is equal to BX in the I direction plus BY in the j direction plus bz in the k direction. If I wanted to dot a into b, so a dot b, all I have to do, since this direction rule I just told you about applies, if they're in line with each other, they multiply by 1, or they're equal to 1. If they're perpendicular, then they equal 0. That means that I dotted into I gives us 1. J dotted into J also gives us 1. And K dotted into K also gives us 1. Anything else gives us 0. I dotted into J is equal to 0, I dotted into K is equal to 0, and J dotted into K, or any commutative flip-flop of that, right? Therefore, all we have to do is multiply AX times BX, add that to AY times BY, and add that to AZ times BZ. There's no I, J, or K anywhere. We're just just multiplying the like components together, and that gives us our new vector, our new scalar quantity. So we get two vectors dotted together, gives us back a scalar. There should not be any I, J, or K on there. Alright, we'll talk about the last way to multiply vectors, and that is the cross product in our next video.